Most modern automated production lines are specialized in manufacturing one specific product. Some systems are able, to a certain degree, to make a number of variants of one product on the same production line. However, the structures and fundamental process flow sheets of these systems are predefined up to a certain degree. Changes or expansions often were not envisaged. Modifications, such as the addition of another station or even of one single assembly step, in most cases must be integrated into the entire system. This is comparatively expensive and often not worthwhile economically. A novel control system can help solve these problems. An agent-based control system for automation was developed by 10 industrial partners, universities and research institutions within the IDEAS EU project, Instantly Deployable Evolvable Assembly Systems, funded by the European Union in its 7th Framework Programme. This is the idea. Mechatronic agents combine into a decentrally controlled system. A mechatronic agent consists of a hardware part, the adapted electronics, and a software part. The agent is a software unit with a defined capability and function. Let us demonstrate, by the example of an assembly line, how an agent-based control system can be employed. In our case, every product to be assembled and every resource, such as all assembly stations, are equipped with an individual agent, as is the transport environment. Each agent is autonomous, carries comprehensive information about itself, and is able to communicate and interact. More complex systems, such as assembly cells, may be made up of several agents. These then constitute a coalition agent, representing the coalition externally. The product agent knows which manufacturing steps are necessary to make its product. This is what it communicates to the other agents as soon as the product enters the assembly line. The product agent then computes the optimum throughput on the basis of the assembly and transport cost data it receives from the other agents. The resource agents, which offer the manufacturing steps, so-called skills, report whether they are connected to the system, what skills they are able to perform, and what capacities are available. The transport agent collects all logistic information and guides the product to the appropriate station. The transport agent always knows what resources are available. The recipe for its product is the basis of the assembly plan to be executed by the product agent. The recipe states precisely the processes needed by the product for its fabrication. The product agent inquires from the appropriate resource about the cost of executing the process. The product agent tells the transport agent, "I need a specific resource." The transport agent tells the product agent how much the transport will be. On the basis of the process and transportation costs, the product agent then decides which resource it would like to go to. The transport agent passes the product to the desired resource. In case of an unexpected event, such as failure of a station, a missing resource, or overloading of a station, the entire system is able to respond. The transport agent responds to the changed situation, it stops the product agent, and negotiation starts again. Subsequently, the product is passed to an alternative station if possible. This ability to adapt to changed conditions is a key feature of the concept worked out. The IDEAS project partners developed a number of software tools in support of the development process. On the basis of this agent environment, The mascot tool is used to build the assembly line and the individual stations. The assembly line is configured by means of drag and drop. Subsequently, the configuration data are communicated to the stations. The workflow editor is used to draft and deploy the assembly recipe of the product agent. While the plant is running, the visualization tool shows the status of the agents and the current status, including the history log file and performance measurement.
From the hardware to the software, everything has been designed to render these systems pluggable. We should be able to resize the system either by making it bigger or smaller to circumvent disturbances or to face the introduction of new products and new product requirements. And this is actually a unique approach. Unlike conventional design, this is designed for self-organization, which means that each module on the system is actually designed to operate with each other module in a seamless way. So no reprogramming is required. It's mainly reconfiguration actions that need to take place.
And the big advantage of IDEAS is that you can change this installation very quickly by plug and work. The system will adapt. It will create the necessary software changes automatically and keep running in a very short time. This in turn means that you can save a lot of investment and work in ramping up a system. You can, in the virtual, simulate the running of the system. You can create new things in the system. And the new dimension is that you have a one-to-one relation to the physical world, which means things you do in the virtual can be applied to the physical world almost without any time delay. And the other way around, changes in the physical world have an immediate change as a consequence in the virtual world. So we hope that the IDEA system will help in that respect to support manufacturing in Europe, and this is why we started this work a long time ago. And as you can see in this laboratory, we have been working on topics related to this intensely. In the national discussion, this is now coined cyber-physical systems. We have been working in these cyber-physical systems for a long time because we understand the one-to-one relation between the virtual and the real to be a big opportunity for the future.